lives Ron Pincassi. So this is the address, and his name is Ron Pincassi. You are welcome. Geometric graph theory. So this geometric thing, it sounds like a nice adjective next to graph theory, but as you'll hopefully find out, in this context, actually, it has a technical meaning, and I will define it. I will use it as a technical term. But I think that first, I need some kind of excuse for speaking here. And about this topic, I gave a series of 10 lectures about geometric graph theory about a year ago, which you can find, the slides you can find on my webpage. And I find it rather hard to sort of summarize the whole idea of this subject, if there is a subject here, in a short time, but I will try my best. So let's start with graph theory. So when graph theory started in the 1930s, then it was kind of clear what the subject was about. So actually the subtitle of D.N.S. Koenig's book that appeared in 1936, which was the first genuine textbook on graph theory, was Combinatorics topologie der Streckenkomplexe, which means that combinatorial topology of systems of segments. So at that time, the fact that we are talking about points and some pairs of points are connected by straight line segments, it was kind of clear. Later on, somehow, in the most successful areas of graph theory, graphs were considered binary relations rather than combinatorial topological objects. And so if you think about it, for instance, extremal graph theory, in extremal graph theory, certainly the actual topology doesn't play much role. Or if you think about Ramsey theory or the theory of random graphs, Streckenkomplexes of straight line segments didn't play any role. In fact, it went to the extent that in 1970, Turan wrote that the graph theory which is relevant for applications belongs basically to logic. And if you think about it, it makes perfect sense. So what is, for instance, the simplest case of Turan's theorem? Well, it says that if a graph has sufficiently many edges, then it must contain a triangle. But triangle is not a geometric object. It basically means that if you have a binary relations and there are many pairs that are related to each other, then you will always find 3 points so that all 3 pairs determined by them are related. So now graph theory really found a number of different applications, but somehow, not surprisingly, in those areas where you really needed some geometric information, it wasn't particularly successful. There was a big change in recent years, in the last 2 decades, from the theoretical front as well as from the practical front, so to speak. First of all, due to the monumental work of Robertson, Seymour, and company, topological graph theory really became a very strong field. However, it is, or at least has been preoccupied to a large extent to drawings of graphs, embeddings of graphs in various surfaces. The other change is the emergence of graph drawing, which is an area of applications where there is a lot of interest from all kinds of people from industry. However, for drawing, actual drawing algorithms that may be used in computer graphics and things like that, now there is also a book about this topic written by these people, but the theory is rather meager. So what has to be understood somehow is the structure of graphs that are actually drawn in the plane in one way or another. And this is the main topic of today's talk and the talk that I am giving tomorrow. Now, there is a strange thing here that although we are interested in all kinds of complicated drawings, figures in the plane, we still have to start with planar graphs. The reason why we have to start with planar graphs is because, first of all, these are the simplest objects. Those are the graphs that can be drawn in the plane without crossing. But secondly, it turns out that almost everything that we'll be able to say about non-planar graphs drawn in the plane will somehow go back to our knowledge about planar graphs, and whenever we discover a little new fact about planarity, we will be able to capitalize on that to a large extent. So this means that planar graphs really play a central role here. So they are fairly well understood, have been for a long time. So let me just summarize that what are those things that we all know about planar graphs and we use about that. The first one is, of course, Euler's formula, the relationship between the number of vertices, edges, and faces of a graph. Now, the second one is more recent than that, is Kuratowski's theorem, which gives a very nice characterization of planar graphs. A graph is planar if and only if it doesn't contain a subdivision of K5 or K3C, or in an equivalent, almost equivalent formulation, if it doesn't have a minor K5 and K3C. Minor, a graph has a minor, K5 minor, if actually the graph can be contracted. By edge contractions, we can get a K5 from the graph. Edge contractions and, I guess, edge deletions, but in this case, deletions are not needed. So the subdivision of K5 is, that's kind of self-explanatory. So if we have here is a K5, a complete graph is 5 vertices. And if we add some extra vertices on the edges that are disjoint for different edges, then we got a subdivision. Of course, if the graph contains, a connected graph contains such a subgraph, a subdivision of K5, then it also can be contracted to K5 because we can contract these edges one by one. So this is Kuratowski's theorem, which has a kind of funny algorithmic aspect. Namely, if you really want to check whether a graph is planar, in principle, there are a lot of things to check there, right? Because in the graph, for any set of 5 vertices, you really have to check whether they induce a subdivision of K5, which is a non-trivial issue. Nevertheless, surprisingly, there is a linear time algorithm for deciding planarity, whether a graph is planar. And I should emphasize this because there are so few efficient algorithms and problems of this kind for which actually efficient algorithms can be used, that this is one of the very few and nice exceptions. Now here is the third fact that we need, which is somewhat less known. This is the Hanani-Tat theorem. So the first proof that I understand comes from Tat's paper, but Tat refers to another paper by Hanani under the name of Chojnacki. However, I couldn't find in that paper anything remotely similar to that, but in fact I didn't understand the main theorem in that paper either. But I think that this is now the standard reference. It's a Hanani-Tat theorem. So what is the theorem? The theorem gives another characterization of planar graphs. A graph is planar if and only if it can be drawn in such a way that any two edges cross an even number of times. Now, of course, if the graph is planar, then you can draw it in such a way that no two edges cross at all. So 0 is an even number. But the other direction is less trivial. So if you are able to draw the graph so that any two edges cross an even number of times, then actually you can draw it without any crossing. Now, you look at this theorem, and it kind of offers itself as a natural approach that imagine that we have two edges that cross an even number of times, say twice. Well, then why don't we just deform one of the edges, this one for instance, so that we avoid crossings at all. So it seems that if this theorem is true at all, and it is true, then there must be some kind of a natural algorithmic approach to it, which proves it, some kind of a topological operation, or as topologists like to say, that surgery, whatever, that will get rid of the crossings. Now, if you look at the statement of the theorem, there is one word here that I didn't emphasize. In fact, the Hanani-Tat theorem, at least Tat's version, is slightly stronger than what I said. Because what happens is that in order for the graph to be planar, it is enough to assume that any two non-adjacent edges cross an even number of times. So if two edges go out of the same vertex, we don't care. Now, there is a sentence in Tat's 1970 paper which says that something like that: we are taking the view that crossings between adjacent edges are trivial and easy to get rid of. Now, that's a very interesting statement, a very sort of, it's very hard to translate it into mathematical content, but Tat was a very clever guy. Unfortunately, we can't ask him anymore what he meant. It seems, after you play with these concepts a little bit, that this is exactly the crux of the matter. We don't know how to get rid of. Maybe he may be right, but we have no idea how to get rid of crossings of adjacent edges. So, and as a consequence, at the moment, we don't have any algorithmic proof of this theorem. So any proof that is along that lines, that you look at the drawing and you get rid of the crossings. In the weaker form, if you assume that any two edges cross an even number of times, then there is an almost algorithmic approach which I will try to sketch soon. Okay. So how do we prove the Hanani-Tat theorem? Well, the proof is unfortunately via Kuratowski's theorem. So this means that we assume that any two non-adjacent edges cross an even number of times, and then we prove that under this condition, the graph cannot contain a subdivision of K5, and it cannot contain a subdivision of K33. Somehow, I mean, I don't want to give the proof, but it is not very surprising that parity enters the picture here. And the reason behind is the Jordan curve theorem. Because obviously crossings occur between certain edges if they are kind of unavoidable. If we get from the interior of a region to the exterior of it, then there must be a crossing. Actually, there must be an odd number of crossings. That's what the Jordan curve theorem says. So, for instance, this is a false and very schematic proof of the first fact. So, I assume, for instance, so you like to prove that if any two edges cross an even number of times, then it cannot happen that the graph contains a subdivision of K5. Okay, so assume that it contains a subdivision of K5. So if it contains a subdivision of K5, then these blue things are the 5 basic vertices. Look at those 5 basic vertices. Look at one of them. And this one is connected to the other 4 vertices by certain paths. Look at those 4 paths. These paths have a cyclic order. And take in this cyclic order 2 opposite vertices. We know that the graph contains the subdivision of K5, so these 2 vertices are also connected by a path. Now, look at this yellow region, which is determined by these 3 paths. Now, obviously, this dark blue path here enters the interior of this yellow region. So since every edge of it must intersect every edge of each of these 3 boundary pieces an even number of times, therefore, if it enters the yellow region and it crosses the boundary an even number of times, it must end in the yellow region. So this point must be in the yellow region. Similarly, if you look at this edge here, which is opposite to that, this starts in the white region. It goes out to the outside. By the same argument, it must intersect, this path must intersect every single edge of every boundary piece an even number of times. So altogether, this path intersects the boundary an even number of times. So the other endpoint must be outside. But there must be a path connecting these 2 vertices. And that path must also cross the boundary of that yellow region an even number of times, which is impossible. Now, this is almost a proof. You have to sort of massage it.
What was the definition of the yellow region?
Well, this is exactly the weak point of the argument. You know, there are this path, and this path, 3 paths. Now, 3 paths, if you put them together, they can sort of determine a more complicated region. For instance, this is a slight complication. Then you know how to color it, right? So you just use a chessboard-like coloring, and that will be the yellow region. But
you assume also that adjacent edges cross an even number of times.
And I also assume that adjacent edges cross an even number of times. That's the other weak point. So I could as well tell you the whole proof now if you are so alert. Yes?
Any issue of self-crossings at all?
No. That's the only problem that doesn't occur here. But anyway, so basically, if we use Kuratowski's theorem, then the Hanani-Tat theorem reduces to some kind of a finite proof, and certainly it doesn't give us any clue about an algorithm. Let's not worry about it for the time being. Now here I also have to mention quickly that this kind of argument is not uncommon in topological graph theory, if you wish. For instance, one of the celebrated theorems of Robertson, Seymour, and Thomas says about three-dimensional drawings that it characterizes graphs that can be drawn in three space without a link. What is a link? A link is when you have two cycles that are linked. Well, not a very precise definition, but I hope that you don't ask questions about it. So a graph has a linkless embedding if and only if, this is one of those Robertson-Seymour type theorems, if it has no minor, it has a characterization by minors, no minor belonging to the Petersen family. The Petersen family is a family of 8 graphs. One of them is K6. Actually, I can show you what the graphs are. These are the 8 graphs. And it's called the Petersen family because one of them is drawn in a funny way, but it is actually a different kind of drawing of the famous Petersen graph. Now, all of these graphs in the Petersen family can be obtained by K6. The complete graph is.
The Petersen family is Petersen graph with delta Y.
Exactly. So what happens is that you take the Petersen graph, or as a matter of fact, you take K6, and a complete graph is 6 vertices. And what he referred to is that you do the following operations, which is called the delta Y operation. So if you have a triangle, then you can replace a triangle. I guess that I should draw it the other way around, but then it doesn't look like a Y. By these 4 vertices, or if you have a vertex of degree 3, you can replace it by a triangle. So whatever you can get from K6 in this way, those are the graphs. One of them is the Petersen graph. So it turns out that if none of these graphs have a linkless embedding, and if you do this so-called delta Y operation, that doesn't change this fact. But this can be checked fairly easily. It was noticed actually much earlier by Sachs. Now, why do I mention it here? Well, it has several reasons. You will see that, strangely enough, this Petersen family enters the picture later. But the argument is, again, a classical argument in parity. So, for instance, just look at K6. Why can't you draw K6 without a link? So no matter what I claim is that no matter how you draw a complete graph with 6 vertices in 3 space, you always find 2 linked triangles. And let's just simplify the drawings. We only consider, for the time being, straight line drawings. So you take the points in general position, if you wish, and then you connect everybody with everybody. And no matter how you do it, how you arrange your 6 points, you always find 2 triangles that are linked. Now, the proof is the following. That we start with our favorite example. For instance, this is, I think, an octahedron or something like that. These are the 6 points. And one specific example, and in that specific example, you check what happens. You find 2 triangles. In fact, you check something more. Because if you look at K6, it can be partitioned into 2 3-element sets in several ways, and they are either linked or not linked. You count how many of these partitions result in linked triangles. And for this example, there is just one pair. So 1. It's an odd number. And now what you start doing, you start pushing the points around. And you see that whenever something changes, the number of linked pairs will always change by 2, by an even number. So you can never end up with 0. You will always find 2 linked triangles. So why is that true? By the way, it is pretty visible that why it is true that the number of linked pairs always changes only by an even number. Because when do things change? Things change when you move the points around, when 2 edges happen to cross each other in 3 space. When they happen to cross each other, so for instance this one and this one, then here you have they crossed each other. There are 2 other points. We don't know where they are. So let's take this point and add to this edge, and let's take the other point and add to this edge. Now these 2 triangles may be linked or maybe not, but certainly this relationship will change when we move the 2 edges across each other. So if they were crossed, then they won't be. However, there are 2 such pairs, because if you think about it, if you have this pair of crossing edges, then we can associate with this edge this vertex, or we can associate with this edge this vertex. So there are 2 different pairs of triangles. And in both pairs, the situation will change at the same time. So it can change only by an even number.
Intentional that your drawing shows K6 minus 1 edge? Oh, it's minus 2 edges.
I guess so. But I forgot my intentions, you see.
2 is an even number.
Okay.
Being linked, I guess you interpret as having odd linking number.
Yes. If you want this argument to work for the general case when there are no straight line drawings, then you have to define the linking number and odd even linking number precisely. Thank you. Now there are other important characterizations of planar graphs, but let me just mention, without going into, without saying anything, one which got a lot of attention recently, the Colin-Daverdier parameter, which is defined in terms of higher dimensional realization of a graph. So anyway, for every graph, we can assign a parameter mu, which is called Colin-Daverdier parameter, in a fairly natural way. But if you don't know that, then it doesn't make sense to give you the formal definition now, because it will look like a mess. And it turns out that a graph is planar if and only if this parameter is at most 3. Now, it was quite an important achievement a couple of years ago, kind of combined work of Lovaas, Schreifer, and on the other side, because the theorem has really 2 ingredients. On the other side, Seymour, of course, and company, that they actually proved that what happens if the Colin-Daverdier parameter is 4. It turns out that a graph has Colin-Daverdier parameter or invariant at most 4 if and only if it has a linkless embedding. And now nothing moved since then. It is one of the interesting unsolved problems to decide what's next. So if this parameter is at most 2, then the graph is outer planar. It is like a triangulated cycle. If it is at most 3, then it is planar. If it is at most 4, it means that the graph has a linkless embedding. And everybody would like to conjecture that at most 5 means that it has a knotless embedding. But this is just wishful thinking, because somehow we don't really know what those topological parameters are that may enter the picture here. So there is really no good, at least I don't have any good intuition behind this conjecture. Okay. Now, there is one more theorem that one has to mention, and in fact it was mentioned under different names before, well, related to polytopes, which I'd like to call Fari's theorem, because Fari was Hungarian and a very nice guy. But probably he was the last one who proved this theorem in this list. But all of these people came much after the theorem was really known as Steinitz theorem or whatever. So anyway, the meaning is it's a very useful theorem, especially people who are interested in graph drawing algorithms are very much interested in it, that every planar graph has a straight line drawing. Now, of course, what graph drawing people were really interested in would be a straight line drawing on a grid. Oh, I don't delete that. So this means that that we look at a screen. The screen is made out of pixels, and we would like to have, so here is our favorite planar graph, I don't know. And we want to draw it so that the vertices are mapped into grid points, and the edges are characterized, the edges are drawn by straight line segments. And obviously, we would like to use a small size grid for doing that. It was, in fact, conjectured by Tarjan and Rosenstiel that if you want to embed all planar graphs of size n, then you need an exponential sized grid. But the truth is that the situation is much better. And in fact, every planar graph is a linear time algorithm, can be drawn on an n by 2 by n by 2 grid. So a planar graph is n vertices, has a straight line drawing on a small grid, which is good news. Unfortunately, if we want to go beyond planarity, so if you want to draw, for instance, order types, other point configurations on small grids, then we are lost, as it was proved in a paper of Goodman, Pollack, and Sturmfels many years ago. But for planar graphs, there is a nice drawing on a small grid. Now, yes.
If you have a vertex of degree more than 4, how do you draw it on a grid?
Here this is not so this is not this kind of a drawing where an edge is drawn like this. You know, the edges are drawn by straight line segment. So you can have a vertex which is connected to an arbitrary number of other vertices, just not along the same line. But yeah, thanks for pointing out, because that's also a sort of field of graph drawing where. But then we can draw only vertices of degree at most 4.
What's
yes.
the reference for the n-2?
The n-, this was proved by Ricky Pollack, Hubert de Frézy, and myself, and independently a little later by Schneider. we had only an n log n algorithm, and then I think that the log n was just our ignorance in data structures. So it is really a linear time algorithm. So let me tell you a very simple and stupid proof of the Fari theorem, which is actually one of the main ideas behind one of the proofs. So clearly, if you want to prove the Fari theorem, it is enough to prove it for triangulated graphs. So every planar graph can be triangulated. So if you can draw triangulated graphs by straight line segments, then you can draw any planar graph by straight line segment. Now, if you have a triangulated planar graph, then you can always number the vertices of that planar graph in such, well, by 1, 2, 3, 4, n in such a way that, so for instance, this is 1, 2, 3, so you start with a triangle. And then later on, if you have already defined the first k vertices, then the first k vertices will induce in your planar graph a simple, nice connected region. So if you look at your planar graph G, triangulated planar graph, and you look at the first k vertices, then the first k vertices, what the first k vertices induce is always a simple region. So this means that its boundary cannot even touch itself from inside. It's really a simple region. And the next vertex, vertex number k plus 1, is outside of this region and is connected to a number of adjacent vertices on the boundary of that region. So this is the k plus first vertex, and now if I have color chokes, and I do have, then now the first k plus 1 vertices will induce this region here, and the next vertex, vertex number k plus 2, will be connected to some adjacent vertices along this new boundary, and so on. So you can always number the vertices in such a way that you are always adding a new vertex, which is connected to a number of adjacent vertices. Okay, so if you believe me, and why wouldn't you believe me? Then now you can do all kinds of strange things with Fari's theorem. For instance, you can add an extra condition. Not only I will draw my triangulated planar graph in such a way that every edge is drawn by a straight line segment, but moreover, I have vertex 1, vertex 2, and at every given time, the sort of contour of the part that I have already drawn has an x monotone upper boundary. And then I can keep this property alive. Why? Because now, if I do it by induction, then I have to add the next vertex, k plus 1. So the next vertex has to be connected to some vertices here. For instance, it has to be connected to this one, to this one, to this one, and to this one. Well, all I have to do is that I look at this sort of strip here, and I put a point high enough up in the sky that can see all of these vertices and connect them. And then the new boundary will still be x monotone, and so on. The same way I can keep the contour convex, and sort of developing this idea further, it requires a new element. One can actually end up with this grid grid drawing on a small size grid. Now, here I have to mention an open problem, which is kind of an upsetting open problem. At least it upsets me, and several people try their hands on it. The question, I think, was first asked by Bojan Mohar. So assume we have all planar graphs with n vertices. And we want to draw them on a universal point set. We want a point set, a small point set, as small as possible, so that each of those graphs we can draw on that point set. What do I mean by that? I mean that we can assign, we have a universal, we want a small universal point set, so that every planar graph is n vertices. We can assign locations in this point set to the vertices, so that if we connect the corresponding vertices, then we do not create any crossing. Now, clearly, this thing shows that there is such a universal point set of size n minus 2 square, right? Quadratic. But is there one whose size is linear?
Just take endpoints in general position in 3 space.
Yeah, sorry. In the plane. From the other direction, well, obviously we need at least n points, right? Because we need a location for each of the points. And there are all kinds of claims that partially by us, that actually this can be improved a little bit to 1 plus epsilon times n. But the only published proof is that you need at least n plus square root of n vertices. Now here the square root of n can certainly easily improve to n to the 2/3, but this may have nothing to do with the truth. So my conjecture, if I would be forced to make a conjecture, my conjecture would be that 100n points should be sufficient. But the proof of this grid argument, both proofs are so structural that you can't leave out any of the grid points. I mean, you can leave out a couple of them, but not many. So I find it a challenge to decide whether here the truth is linear or not.
How do you embed K3 in a 1x1 grid?
Well, this is a very good question. I guess then you have to stretch the definition, and you will have to say that a 1x1 grid is this one. So I guess that if I want to be honest, then instead of m minus 2 square, I should write m minus 1 square. The question is that how do you measure the size of a square? By the number of vertices along that side or the length of it. And it's very hard to sort of stick to one definition, but thanks for pointing out. Now, of course, when we come to Fari's theorem, it's impossible not to put, at least for a second, here the Köbes theorem, which, by the way, was also proved much before Fari, Trotter, Wagner ever thought about the problem, which is a far-reaching generalization of that. So every planar graph can actually be represented by touching disks. And of course, if such a so-called coin representation exists, then if you just connect the centers of the coins, then you get a straight line drawing of the corresponding planar graph. The bad side of Köbes theorem is, of course, that it's analytical rather than algorithmic. However, the analysis part has been completely combinatorialized. And this was quite an important achievement of Schramm, Colin de Verdier, and company. Now, I promise that I will tell you something about the Hanani-Tat theorem. I will sort of sketch a proof of it, which can be considered algorithmic, at least in the case when any two edges cross an even number of times. So let me repeat the theorem. So the theorem is that, in the form I'd like to prove it, if any two edges of G, a graph drawing, cross an even number of times, then G is actually planar. This means that the graph can be drawn without any crossing. So the proof that I will tell will contain a number of small lies, but actually those small lies can easily be fixed. So the message, I think, that should be clear. So let's start with a drawing of the graph G in the plane with this property, any two edges cross an even number of times. And let's get rid of the crossings completely. How do we get rid of the crossings? Well, the usual way, cheating what topologies do, that wherever we see a crossing, actually we introduce a little bridge. We attach a little bridge to the plane so that it's like an overdrive. We avoid the crossing. Okay. So now, of course, we have a drawing of the graph on which has no crossings, but unfortunately it's not on the plane, it is on a more complicated surface. Now we make this surface even more complicated. How? That we look at this, oops, you are not supposed to see that, secret. So we look at the plane with the bridges attached to that, and the green thing is, the green edge is, this is the drawing of the graph. And then on that complicated surface, plane plus bridges, we actually look at a little epsilon neighborhood of the edges. So this is like, so what I'm doing now is, in another way, is that I take a pair of scissors and I just go around the edges, and in both directions, at a distance epsilon, I cut off whatever is there. So what happens now is that I get a mess. From the plane, I get only pieces of roads, so to speak, around the edges. Plus, I have the bridges, and the width of the bridges will be epsilon. So locally, the situation will be nice, because locally, when I look at a vertex, then from that vertex, if 4 edges go out, this means like 4 roads going out, or four bells, or something like that. So it is just a union of, a complicated union of bells. However, this surface that I get, which is the union of these belts or overdrives, overpasses, I denoted it by S1, it is not that ugly. What happens is that if you look at the boundary of it, which is these purple arcs, that the boundary consists of a finite number of closed cycles, right? So what happens here? So let me just follow one segment of the boundary, and then I get close to a vertex, and I continue on the next belt that goes out. And after a while, finite number of steps, I will have to get back to the original one. And then I start a new one. So there are a finite number of simple cycles. So what do I do now? Well, the usual things what topologists do, that I attach a disk to each of these purple boundary curves. So in this way, I sort of, there was a hole there, and I kind of fit a topological disk on that hole. So in this way, of course, I get a new surface. Now, this new surface has no boundary, right? Because wherever there was a boundary curve, I put a disk on it. And since originally, so this new surface I call S2, since originally my graph was drawn on this previous surface S1, which was the union of these belts, and S2 contains that surface, now I have a drawing of my graph on this new surface S2. So it suffices to prove, suffices, sorry. I hope that was the only problem with my pronunciation. Now it is enough to prove that the surface S2 that I got is the sphere, right? So if it is the sphere, and then I found a drawing of my graph on the sphere without crossing, so it must be a planar graph. So how can we prove that this is the sphere? Well, actually, to prove that it is the sphere, we need some topology, but almost zero topology. So what we need is just the following characterization of the sphere. The sphere is the only oriented surface that has the property that any two closed curves cross an even number of times, right? So if you look at the torus, for instance, then you can have a cycle around the torus, another cycle, and they will cross only once. So what we'll do is that we'll prove that if we have two closed curves, that they always cross an even number of times. So any two curves, closed curves, on S2 cross an even number of times. Yes? Zero. Zero is an even number. Yes, yes. Yeah. This is what you'd like to get eventually. Okay. So the first thing is, so what is the surface S2? Again, we have this complicated surface and we put the disks on it. So the first thing is that, let me just draw one. If I have purple, then I will use it. Okay, this looks like purple. So let's just look on that surface one original boundary piece. And on this boundary piece, you see we attached a disk to it. And let's just look at that. This is on the surface U, surface S2. And now we look at two closed curves. So consider one of those closed curves. So one of those closed curves, well, this one of those closed curves, we actually enter this new disk that I added to the surface. And it actually may enter several times and leave. But I don't want these complications that happen in the middle. But luckily, I can forget about those complications. Why? Because if I look at this closed curve, then I can just push those pieces of these blue closed curves that are inside this disk that I added to the boundary. This has to be done with some care. But it's not very difficult to see that these are local changes, and if previously it was true that, that these local changes, if I had two closed curves, they don't change the parity of the intersections between the different curves. So if I had an orange curve here and a blue curve, and I pushed the part of the orange curve which was inside to the boundary and the part of the blue curve which was inside to the boundary, then the parity of the number of intersections didn't change. This is because when I had two intersections before, suddenly I got 0. Here there is really no cheating. So, okay, so what happens afterward is that, that I have two closed curves, and I can assume that those closed curves actually go along the edges of this drawing. I don't have to look at the complicated surface, just along the edges. Okay, so they go along the edges of the drawing, but if they go along the edges of the drawing, here there is a little difficulty, of course, because they may use the same piece of an edge several times, so you have to take care of that. But anyway, just concentrate on that. And now look at those modified orange curve and blue curve that go along the edges. And project them onto the original plane. When you project them onto the original plane, then of course you get two closed curves in the original plane. Those closed curves will cross an even number of times, because any two closed curves in the plane cross an even number of times. The question is that how much did the situation change when I actually lifted them up? But when I lifted them up to where they were, then the changes I made were always even changes. Why? Because assume that two pieces crossed each other somewhere, right? Then obviously they go along two edges of the original graph. After I lifted them up to these bridges, then I got rid of the crossings between the edges. And since any two edges crossed an even number of times, the number of crossings I deleted was always even. Yes?
I mean, sounds okay, but I mean, I just think about this step. You can get two linked cycles if you do these bridges, and then when you close it with this, you close the holes with this, you get something like those. And if I'm not mistaken.
You can think of this in an abstract way. You don't have to do it in R3, I guess.
Yeah.
You can do it in R4 and then.
Yes. Yeah. Well, I mean, I told you that I will be lying, and this is one of the details, of course, that you have to define, and there are other things that you have to sort of make more definite. For instance, when I reduced my cycles, then it is possible that actually a curve will turn back in the middle of an edge. So I have to pull them back, and there are all kinds of little unpleasant things that you have to take care of. But this is basically the message of the proof. So this means that when you take two cycles, those two cycles you can reduce so that they go along these green edges. After I projected those two cycles in the plane, then the number of crossings will be even because I am in the plane. And when I am lifting it up, when I am doing these overpasses, that any pair of edges, in any pair of edges that I may have used, I actually got rid of two crossings, or an even number of crossings, because of my condition. So this means that this proof very much uses the fact that any two edges cross an even number of times. Not just as it was stated in the Hanani-Tutt theorem that any two non-adjacent edges. I really needed the full strength of the assumption, otherwise the proof is dead. The idea is, by the way, the idea of this proof originates with Nikolaevsky and Kans.
You prove something stronger
Yes,
correct.
precisely.
With the weaker hypothesis, you might have to rearrange them.
Exactly. Okay. So this is the Hanani, the so-called algorithmic proof of the Hanani-Tats theorem in at least this form of the Hanani-Tats theorem, this weaker form of the Hanani-Tats theorem. And since today we spent so much time with graph drawings in the plane and planar graphs in particular, and tomorrow I really want to concentrate on geometric graphs, and I will give you the precise definition. I'd like to close this talk by a very nice open problem, which is the following. So, can we represent? So we have seen that planar graphs can be represented in many ways. In particular, the Koebe representation gives a disk representation. But now, I want to represent the vertices of the planar graph not by disks, not by circles, if you wish, but by real segments or pseudo-segments, if you wish. Pseudo-segments, what is pseudo-segments? That any two of them cross precisely once. But the nicer thing would be if they would be real segments. The question is, can you represent them, the vertices, by real segments, say, so that two real segments intersect if and only if the corresponding vertices are adjacent?
You mean every two of them intersect at most once?
At most once. Touching is not allowed, you see, because if touching is allowed, then you take the coin representation, and where you can say that in the coin representation the circles are closed curves, but then you can cut them. But touching is cheating. So either you assume real segments, or you assume that they are pseudo-segments in the sense that any two of them, if they have a point in common at all, then they cross properly at that point. Now, this is known for bipartite planar graphs. There are claims by Hubert de Frézy and Patrice de Mendes that actually they can prove it also for three colorable planar graphs, but it's not known in full generality, and it may be false, actually.
You can dualize a planar graph. How do you dualize one of these configurations?
Is it not to be not true for segments? Real segments?
No.
So the three
As far as I am concerned, the proof for the three colorable case, I am not sure if it uses real segments. Maybe, well, since I am not sure if the proof is correct, therefore I am not sure if it uses real segments, I guess.
The converse must be false, right? You can get any kn for any n in this way.
Yeah, the converse certainly. I mean, you can have a complete graph, yes. So it's one difficulty is that somehow, if you look at the crossing structure of segments, that in a way it's not natural to bring in planar graphs. The trouble is that this problem was raised by some people who needed it for industrial applications, and they couldn't care less whether it is a natural notion or not. But you know, as it happens with problems, often happens if you think about it for 1 day, 2 days, 3 days, after a while you will think that it is a natural problem. So thank you very much for your attention.
Okay, more questions? So I guess the usual way to show that a connected surface is a sphere is just to count the Euler characteristic. Is that not easy to do in this case?
It is easy. I was hoping that it is nicer, but no, it is easy actually. I mean, not very different. I find it more easier to swallow.
Another question.
That's a good question. Many people ask this question. No one has a clue. For me, it is a total mystery. So since I don't quite understand the structure of it, I wouldn't even conjecture anything. It's yeah, it would be nice. Yeah.